So the last portion of chapter 3 is limiting reagents and excess reagents. So we're still doing stoichiometry, which means that we're still talking about reactants and products and equations and whatnot. Okay, so now we need to deal with if you have more than one starting material, all right, which means if you have more than one reactant, then you want to make sure that the reaction works but without wasting any chemicals. So you want to make sure that you calculate properly as to how much you need. So if you just kind of work with two reactants of any amount, one of them is going to be in excess and one of them is going to limit the reaction. What does limit the reaction mean, or limiting reagent mean? It means that when it is finished, then you don't have any more reaction going on because there is nothing to start with. Okay, so if I were to bring up sandwiches again, then let's say that you have 6 slices of bread, 2 slices of cheese. Well, once you've one slice of cheese for 2 slices of bread, well, then you're stuck, right? After making 2 sandwiches, you only have bread left, you don't have any cheese left, okay, at that point. So which means no more sandwiches. So at that point, the cheese is your limiting reagent and your excess reagent is bread. So that was an easy calculation for you to do. But here, when you're working with reactions, you have to do just a little bit more calculations, okay, in those cases. So in limiting reagent problems, we have just a little bit of a longer calculation to do. So how do we do this? Okay, so first of all, how do you even know that it's going to be a limiting reagent problem? All right, so the way you know this is that when you have 2 or more reactant quantities given to you, you know you have to work in limiting reagent. Okay, now the problem is going to be set up just like you do for stoichiometry, so there is nothing different over there. Okay, so the way you solve stoichiometry and percent yields and whatnot, it's the same thing. Okay, the setup is the same. It's just that now, because you have 2 quantities given to you, you just have to do it twice. Okay, that's all. So that's how you know that you have a limiting reagent problem. Okay, when you have 2 reactants and both of the quantities are given to you. How do we determine the limiting reagent? I'm going to show you when we do the calculations, okay, because you need to calculate the moles of each of those to figure it out, okay, not the grams. Sometimes you don't need to go all the way to the grams. I just go up to the moles and then we figure it out, okay. And then we figure out the percent yield, and if we need to, we'll calculate for excess reagent also. Okay, so in the case of sandwiches, it was easy for us to do, but for calculation purpose and equation, it's just a little bit different. Okay, so that's what we have to do. So let's start with problems, because the best thing is to solve some problems and see how it works. So here is one with magnesium that is used to prepare zirconium metal. So here is a displacement, a single displacement problem where you're displacing zirconium using magnesium. And how many moles of zirconium metal can be produced from a reaction mixture containing 0.2 moles of zirconium chloride and 0.50 moles of magnesium? So first, let me tell you that we are working in moles, right? Because we don't have any grams given to us. So which means that I'm just trying to introduce you to the concept of limiting reagent, okay? We're not talking about grams yet. It's just about mole ratios and moles and how to set up a problem and how to understand it also. So here is the reaction again, and you know me, I write the reaction out and I write the quantities underneath it. So here it is. So zirconium chloride we have 0.20 moles, and then magnesium is 0.50 moles. And then we are trying to figure out how much zirconium we are going to form. Now, since the quantities are in moles, we don't have to worry about calculating any masses, okay? Also, the answer is going to be in moles, so we don't even need the mass of zirconium, okay? So we are fine with just working with moles. So I need you to understand the concept of limiting reagent here. So you have the moles of zirconium chloride, and then you do the mole ratio to zirconium. So zirconium chloride to zirconium is 1:1. So 1 mole is to 1 mole, okay, of zirconium chloride. That gives you 0.20 moles of zirconium because it's a 1:1 ratio. With 0.5 moles of magnesium, the mole ratio of magnesium is 2:1 to zirconium. So now magnesium goes down here, zirconium is up here because you're calculating for zirconium. So now 0.5 divided by 2 gives you 0.25 moles. So now you look at both of these. So if you were to use 0.2 moles of zirconium chloride, you will get 0.2 moles of zirconium. If you were to use 0.50 moles of magnesium, you will get 0.25 moles of zirconium. But since you're using both of these quantities, which one is going to win out? Which means which one is going to run out first? Whatever is the smallest mole ratio of the product, that's what's going to run out first. So you compare the 2 moles that you get for the product, and whatever is the smallest one, that starting material is your limiting reagent. This is zirconium is not the limiting reagent, that's the product, okay? Your limiting reagent is the smaller quantity that you started with, but you can find this out only after you do the mole ratios and you figure out how much product you're getting. So just going up to moles can help you out, okay? You can convert this to grams also, but what's the point? You can answer right here without going to grams, okay? So you're saving yourself some time. So that is how you figure out limiting reagent, is by calculating up to mole ratio of the product and then seeing which one is the smaller number of moles, okay? So let's go ahead and do another problem. So in this case, what are we doing? Answer the following questions when 7.5 grams of oxygen reacts with 5 grams of hydrogen gas. What is the limiting reagent? What is the theoretical yield of water? And calculate the amount of excess reagent left. Oof, too much to pack, okay, in there, or unpack, you know, in this little question. So first of all, we are not even given any equation, right? So we have to do so much over here. So the first step is going to be write the equation, right? Because if you don't have an equation, we don't have anything. We are going to have to find molar masses because we have grams given to us. So if you have grams, then you have to find moles, which means you need molar masses, okay, for everything. Then we're going to continue on from there. We'll find the moles of water, which is the product, okay? So remember, it says what is the theoretical yield of water? So water is the product. So we're going to find the moles of product from both of the starting materials, and then we'll figure out how much water we'll get from limiting reagent, whatever the smaller number of moles is, okay? Step 1, reaction. So here is the balanced equation. So again, remember, hydrogen is not H, it's H2, and oxygen is diatomic as well, and then here is water as a product. So once you balance the equations out, these are the coefficients you get. And then here is the equation that I write in my way. So I know that I'm starting with 5 grams of hydrogen, 7.5 grams of oxygen, and I'm trying to figure out how much water I'm going to need. So these are the basic things. Like even if you start solving a problem with some of this basic stuff, at least you start getting warmed up, you know, like, okay, I'm getting warmed up with the problem. As you calculate the molar mass, hydrogen, oxygen, water, right? So you have some of the stuff done. So now the step 3, which is the main part over here, this is the bulk of the problem, is you have to find the moles of water formed, okay? So as remember, I said here moles of water, not grams of water, moles of water. So you take both of these things, okay? You're gonna do the same calculation with hydrogen. You're going to do the same calculation with oxygen. So when you do it with hydrogen, you're going to use the mole ratio of hydrogen to water. When you do it with oxygen, it will be oxygen to water. Okay, so it's the same stoichiometric method. And what was the stoichiometric method? If you remember, it's going to be grams to moles, then to mole ratio. And after that is usually grams, right? But I'm going to wait for that because I need the mole ratio first to the product. Okay, once I have the mole ratio to the product, then I know what's my limiting reagent, because the first thing I need to know is my limiting reagent, okay, before I can go on with calculating grams. Okay, so now let's look at what we have here. So 7.5 grams of hydrogen, convert that into moles of hydrogen. And then moles of hydrogen to moles of water is 2:2 mole ratio. So 2 moles of water to 2 moles of hydrogen. Okay. And again, remember, if you feel like crossing this out, so you have your package as well. You can cross that out in there. And so grams and grams, moles and moles, you're left with moles of water, and that's moles of water, okay? So then for the other part here, for the oxygen, same kind of thing. So grams of oxygen converted to moles of oxygen, and then with the mole ratio. So the mole ratio of oxygen to water is 1:2. So 1 mole of oxygen to 2 moles of water. And the answer you get is 0.313 moles of water. Now you compare both of these numbers, okay? So the moles that you got for water from hydrogen, and then what you got from oxygen. You need to compare those two numbers and see which one is smaller. And the smaller number is 0.313, which means that oxygen is your limiting reagent. Now, if you look at these two numbers, oxygen is 5 grams. It's a smaller amount than 7.5. So just directly with that, it's not going to matter whether this is a limiting reagent or not, okay? So don't let that determine what your limiting reagent is, okay? You still have to figure out the moles, you still have to do the mole ratio in order to figure out what your limiting reagent is, okay? So limiting reagent is anything that will give you the smaller amount of product, which means that hydrogen is the excess reagent, okay, in there. Okay, so what is the limiting reagent? One problem solved, okay, that our limiting reagent is going to be water. Now, what is the question here? How many grams of reacts with hydrogen gas? What is the theoretical yield of water? Once we know that this is the limiting reagent, it means that this is the amount of water we are going to form. So which means that we're going to use these moles to find the amount of water, okay? I am not going to be able to come back to this slide, okay? So you have to kind of remember some of this, and if you have a printout of this, you can see it in that, kind of setup you have here. So, because I'm going to have to calculate the amount of excess reagent as well, okay? From here, excess reagent is hydrogen. Okay, so now for finding the mass of water, you just take the limiting reagent that you had and convert it to grams of water. Remember, mole ratio and everything is done. So it's just a matter of converting moles to grams. Okay, so your answer for this is the theoretical yield of water is 5.63. Now for finding the excess reagent, okay, this is also very systematic. This is what I do. Somebody else may solve it a little bit different, and that's fine, okay? If you like that method, you can do that one also, okay? But this is what I do, is I have the moles of water, right? I did that in the previous slide. And so I had this many moles of water. This was the excess reagent. This was the limiting reagent, right? That's what I found. So I subtract the two. So which means that 3.407 moles of water is the excess amount of water I could have formed. I could have formed from what? From hydrogen, because hydrogen was the excess reagent in there. So all I need to do now is work my way backward to hydrogen. So I start with water because I have 3.407 moles of water I could have formed. So I convert the moles to mole ratio of hydrogen. Why to hydrogen again? Because that is my excess reagent. And then all I need to do is convert that moles of hydrogens to grams of hydrogen. Now this number should be less than what you started with for hydrogen, which was I think about 7.5 grams, right? So this is less than that. If it is more, that means your calculation is wrong, because you cannot have more left over because you've already used some of it, right? So you used some of the hydrogen already, so some is consumed, okay, and some of it is left. So that is how you calculate excess reagent, all right? So do a subtraction and then work your way backward. So here is another problem. So let's see. So urea is used as a fertilizer, and we've worked with urea before. It's manufactured from ammonia and carbon dioxide. So here is the same equation again. So in a lab experiment, here we have 10 grams of ammonia and 10 grams of carbon dioxide. So what is the maximum quantity in grams of urea that can be obtained, and how many grams of excess reactant are left at the end of the reaction. Okay, so when they say maximum quantity, if urea, it means that the theoretical yield, okay, is being asked. So see over here, the question does not mention anything about limiting reagent, okay? But it does give you two quantities to start with. So in your reaction, you have both of the ammonia and carbon dioxide that you're starting with. So it means automatically it's a limiting reagent problem, even though the question is not asking you what the limiting reagent is. Okay, so automatically you have to go there. So in urea, that's what we are calculating for. Okay, so the equation is all set. So we calculate the molar masses as usual. And then our next step is going to be to find the limiting reagent. So here is the same calculation again. Take ammonia, 10 grams, convert it to moles of ammonia, and then over here do the mole ratio of urea to ammonia, which ammonia is 2, and then urea is 1. Okay, so 2 moles of ammonia to 1 mole of urea. Keep urea on the top because that's our product, right? So that's what we get. Okay, and then here you have the other one, carbon dioxide, and carbon dioxide converted to moles of carbon dioxide, and carbon dioxide to urea is 1:1. You should still write it, okay? Even though it is 1:1, you should still write the mole ratio. And so there, now the urea is on the top here, carbon dioxide is at the bottom here, and then you get 0.227 moles, okay, of urea. Okay, so now you have to figure out what the limiting reagent is, because now in this case, this one is forming 0.294 moles, and then here you're getting 0.227 moles of urea. So this one is the smaller number. So because this is the smaller number, that's your product that you're going to form, which means carbon dioxide is your limiting reagent. Remember, urea is not the limiting reagent. Urea is the product, okay? So you're forming the smaller moles of the product, and carbon dioxide is your limiting reagent. But anyway, so here we go, 0.227. Now you just have to convert that into grams. Okay, so that's the last step that is shown over here, to take the smaller moles and then convert that into grams. Okay, so then how many grams of excess reactant are left over? So this is another way that we're going to do this. So let's go ahead and see what we're doing here. Okay, so to find the excess, we can subtract the 2. So this is what I have done before also, right? So I subtracted the 2 moles over here, and then you get the moles of urea that could have been made, okay? Excess of the urea, okay? So when you subtract the 2 moles that you got from both of the reagents, then this much more could have been made. And now you work your way backward, because you know that ammonia was the excess reagent. So moles of urea, and then the mole ratio of urea to ammonia, and then convert the ammonia to grams of ammonia. So this then is going to be your excess reagent, okay, that is left over. Again, your excess reagent has to be less than what you started with, okay, to begin with. Okay, so the other way to do this, this is another way of doing this, okay? It's not an old way. I mean, it's whatever way. It doesn't matter if it's old or new. There's just a different kind of way of doing this. So remember, your starting materials are carbon dioxide and ammonia, okay? So what we are trying to do over here is that if you know, once you know what your limiting reagent is, then you know that you're starting with 10 grams of carbon dioxide, because that's the limiting reagent. Now what you need to figure out is how much ammonia do you need, okay, for that. So 10 grams of carbon dioxide converted to moles of carbon dioxide, and you need 2 moles of ammonia for every 1 mole of carbon dioxide. And then once you do the mole ratio, then of course you figure out how much grams of ammonia that is going to be, okay? So it turns out you need 7.734 blah 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 grams of ammonia. Now this is what you would need for 10 grams of carbon dioxide. Remember, carbon dioxide was your limiting reagent. So what happened? You're not going to use all of this. right? So how much is remaining? Because 10 grams of ammonia is what you started with, but you actually need only 7.73. You don't need all of it, okay? Because this calculation is showing you that for 10 grams of carbon dioxide, you need only 7.73 grams, okay, of ammonia. So then all you do is subtract the 7.73 from 10 grams, and you will get the same number as you get here. Now, it depends on how you want to solve your problem. You can do it this way, or you can do it this way, okay? It doesn't matter to me, and you can see that also the answer is still going to be the same, okay? Is that you have the same ammonia, the same amount of ammonia as your excess reagent, okay? In this case, I'm just continuing on with subtracting the moles and then converting those moles back to ammonia. Here you have to do a whole other setup. So it's not that long. You don't have to calculate the masses anymore, right? You already have that. So you just have to subtract, you just have to do the calculation again. So it's up to you which one you find better, okay, for yourself. If you just like the normal stoichiometric way, you can do that too. Then you just have to remember to subtract it here. In the way that I do it, I subtract first because I already have the mole quantities, and then I do the calculation. Okay, so it just depends which way you like better. Okay, that's all there is to it. Okay, so here is another problem, and this one I don't want to go too much into it because I think I've explained two problems. So hopefully now you understand this a little bit, better. I can go through it quickly, okay, so that at least you hear me saying it, but otherwise I think you understand what's going on. Okay, so this one is calculate the percent yield of the product when you have 12.24 grams of the product formed. Okay, so remember when you're calculating percent yield, you need to have the actual yield. Okay, so this is the actual yield formed from the reaction of 11.3 grams of this compound and 13.48 of PCl5, phosphorus penta, or this trichloride. So I'm going to have to correct that also. So bear with me when I just write that over here. So this is PCl3. Okay, so here is our equation given to us, okay, and so it's already balanced. I can see that. So again, write the quantities. Okay, so for the C2H5OH, we have 11.3. By the way, the name of this compound is ethanol. And then PCl3, phosphorus trichloride, is 13.48. That's given here. And the theoretical yield of the product is given to us, okay, 12.4 grams. Molar masses, you calculate them just the way, you always calculate molar mass of everything. And then to calculate the limiting reagent, to find that out, again, take the alcohol, convert it to moles, do the mole ratio of the product, which is 3 to 3. So write it out though, okay? Don't just take it for granted, just write it out. You don't have to put that in your calculator, obviously, okay? Because that's just kind of wastage of time, okay? Just do 11.3 divided by 46.068, okay? And then you get this many moles. 13.48 grams of PCl3. Find the moles of that. Now PCl3 to the product is 1:3. So this calculation you have to do. Okay, so 3 moles of the product over 1 mole of PCl3. So once you do that calculation, you get this number, 0.294. Between these two, 0.245 is the smaller number. So if that's the smaller number, then the alcohol is the limiting reagent. Okay, so if this is the limiting reagent, this is the excess reagent. In this one, do we have to? Yes, we have to find the excess reagent also. Okay, so limiting reagent, okay, is this one. So which means we'll take this one, 0.254, and convert that to grams. You get 15.8 grams, okay, of the product. So this is the theoretical yield. This is the actual yield. I'm sorry, another mistake I found. Oh my Lord. So this is the actual yield. So actual yield is 12.4 and the theoretical yield is 15.8. So in the next slide, I'm going to calculate the percent yield, and we're also going to calculate the grams of excess reagent left. And I'm going to follow my method because I like mine, which is I'm going to subtract these two and then find the excess of PCl5, okay, from there. So the percent yield 12.4 over 15.8, and this is the answer. And then subtraction of the two products. Once you've subtracted, you know this is how much more you could have formed. And once you have that moles, then the product moles, do the mole ratio to the excess reagent, and then convert that moles of excess reagent to the moles of the grams of PCl3. Okay, so moles to mole ratio to grams, and then you have 2.24 grams of PCl3 left over. So this is a long problem. Usually, you know, this kind of a problem can take you easily, even with doing the simplest calculations. It can take you 5 to 7 minutes to do because you still have to calculate everything and set up all the problem, you know. So it does take a little time, so I may not give it to you in a big wholesome way. But it still takes time, okay? So be ready for that. So hopefully I was able to explain to you how to calculate the percent yields and excess reagents and whatnot, okay? So that's kind of, I think, what this is, and I think that's the end of chapter 3 for us. Oof, oh my lord, that was a long chapter, wasn't it?